Okay, here we are, Chapter 17. And Chapter 17 is probability distributions. And really what we're looking at, everything is based off, holy cow, I'm not coughing before the camera starts here. Everything is based off a situation called Bernoulli trial, which is named after a famous mathematician, Bernoulli. There's actually a very famous family of mathematicians named Bernoulli, and this is one particular Bernoulli. Who that is, I don't know. Pick a name for Mr. Bernoulli. It sounds very Italian, so I don't want to say something people go, oh, so whatever. All right, so here's the three conditions that make something a Bernoulli trial. There are only two possible outcomes, success or failure. It turns out you can take just about anything, even you're talking about rolling a die, and turn it into success or failure just by defining what success is. Instead of having a probability model for a die having 1, 2, 3, 4, 5, 6, you can sit there and say, what's the probability of rolling a 4, and define success as being a 4, or an odd number, 1, 3, 5, or a number greater than 3, which would be 4, 5, 6. So you can still determine it to be success or failure. The probability for success, denoted P, is the same for each trial. And previously what we did is we said, oh, this means that they're going to be independent. Because what we defined independence as being set up so that if you've got two different things, the probability of B given A is equal to the probability of B. That's how we define independence. The probability that something happens given that something else has happened is equal to the probability that it happens by itself. Like the probability of rolling a 6 given you roll a 6 has to be equal to the probability of just rolling a 6. And that means they're independent. But here we're not going to call it independence set. We're just going to say the probability is going to be the same. What independence here is going to be, but we're going to change it, we're actually going to call it independent, is that the sample has to be less than 10% of the population size. Because what's going to happen is if your sample that you're pulling from is larger than 10%, then really what you're going to do is you're going to start affecting the probabilities themselves. Under 10%, you're not going to affect it enough that we're going to consider it to be an issue. So we want our sample to be less than 10%. Okay? So why are these conditions Bernoulli? Rolling die? Well, they're Bernoulli because, let's get back up here to these conditions. There are only two possible outcomes, success or failure, depending on what you determine success to be. Probability of success is the same for the die because is a sample less than 10% of the population? It is, because you can't roll this more than 10% of the number of possible rolls it's going to be. Kind of a sticky thing there, but it's true because population could be all possible rolls for that die or all possible rolls for a 6-sided die. Drawing from a deck of cards, there are only two possible outcomes, success or failure, depending on what you determine success to be. Probability of rolling an ace, or drawing an ace. The probability of success is the same if you do this with replacement. Sample is less than 10%. The number of cards you're going to pick is going to be less than 10% of all possible cards. Flipping a coin, certainly possible outcomes, success or failure, heads or tails. Success is going to be the same. If it's a fair coin, if it's not a fair coin, it's still going to be the same. And you're going to flip it less than 10% of all times it's flipped. Shooting basketballs. Yes, two possible outcomes, either you make it or you don't. First shot should not influence the second shot. And here's kind of like a big thing here. Since sample is less than 10% of the population, because if I shoot a basketball too much, I'm going to get tired and I'm going to influence what the probability is going to be. So that's where you have to have a relatively reasonable sample. Pulling M&Ms from a bag, if you've got the infinite bag, yes, it meets all these criteria. Okay? Why are these two not Bernoulli? Because if you're pulling two cards of a deck, saying two cards assumes that you've got your first card still in your hand and then you pull a second card, so the probabilities are not the same. Pulling M&Ms from a bag that has a known distribution, because if I know what the distribution is, then I'm changing the probability. We're talking about the snack size bag, not the infinite bag in the auditorium. Okay, so from there, we've got the Bernoulli family, and then what we have is we have two divisions of Bernoulli. We've got the big Bernoulli family up here, and we've got two offshoots, like a family tree. And the first offshoot is the geometric distribution. And the geometric distribution, otherwise known as a geometric random variable, because it's a distribution, and you're going to pick one, okay, is Bernoulli, and we've got 3 criteria that are Bernoulli, but what we have here is we have one other criteria. Oh wait, I want to break out the big pencil. We've got one other criteria that makes us Bernoulli plus a little bit more, like a square is a rectangle. Geometric distribution is Bernoulli, but a little bit more. And that is this statement right here. The variable of interest is the number of trials required to obtain the first success. And what that means is that we're going to keep going until we get our first success. It could be our first failure, but we're going to keep going until we get what we want. And here's 2 statements right here. But these other 3's are Bernoulli. There are only 2 outcomes, success or failure. Observations are independent, less than 10% of the population. Probability of success is the same for each observation. Okay. Because n is not fixed, there could be an infinite number of x values. We'll look at that in just a second. And the probability histogram for a geometric distribution is always skewed to the right. So let's take a look at that and invest in it for a second here. Let's insert a new page after current page. And let's say that the probability, let's actually have the pen working here. The probability of pulling a blue M&M is 0.3. Now, it's not, but let's go with 0.3 anyhow. Okay? So here's what I'm going to say. Geometric distribution means that you keep going until you get your first, whatever you define success to be. And I'm going to say the probability I'm going to get my first blue M&M. That's success, getting blue M&M. So I say to myself, okay, what's the probability that I get my first blue M&M on my very first try? Well, they basically are saying, what's the probability that I pull a blue M&M? That's going to be 0.3. So, I'm going to label this as 0.3. There we go. 0.3. Okay, now, what's the probability that I'm going to get my first blue M&M on my second try? So I think to myself, okay, if I'm going to get my first blue M&M on my second try, what happens on my first try? Well, that means that probability is, or that M&M is not blue. And what is that? Well, that would be 0.7, the complement. Now, if I've defined success as being P, then the complement would be 1 minus P. So here's what I have. I have an M&M that is not blue. So I'm going to write it like this, just for convenience. I'm going to say it's not blue. And then, because and for more than one event means multiply, I've got a blue M&M. So that's going to be 0.7 times 0.3, which is 0.21. So here I'm going to kind of put some values in here. 0.21 right there. Okay, so what's the probability that I get my first blue M&M on my third try? Okay, so if I get my first blue M&M on my third pick, what's my first pick? Not blue. What's my second pick? Not blue. What's my third pick? Blue. So what we're looking at here is we're looking at M&Ms that are not blue, and not blue, and blue. So, not blue, and not blue, and blue. Not blue is 0.7. 0.7 times 0.7 times 0.3. Okay, I can do that. Really, I can. 0.7 times 0.7 times 0.3 equals 0.147. So we'll come back over here, and 0.147 is just about right there, say 0.147. Okay, so what's the probability that I get my first blue M&M on my fourth? Now, what does that mean is going to happen? That means that I'm going to have my first M&M is going to be not blue, my second M&M is going to be not blue, my third M&M is going to be not blue, and then I'm going to have blue. But you know what? I'm running out of space here. I don't want to have not B and not B and not B and B. So since these are multiplied together, what I'm going to do is I'm going to write this as this. This is not blue, since I have 3 of them, to the third power, times blue. Okay, I can do that. We're going to beep here. So we'll come back in just a second.